I would like to welcome everyone to the MD Anderson Cancer Center Integrative Diagnostic Medicine Case Conference for August 28th, 2020. And here we go. I also entitled the series Adventures in Neuro-Oncologic Diagnostic Medicine. I think that really sets the tone, and I am excited about the program that I have for you today. One quick clarification. I think most of you already know this. I cannot hold the conference on Fridays when I'm on service because of being called a frozen section. I cannot control that, and because of COVID, there's never more than one neuropathologist in the hospital, so I can't have, it's not like the old days I could have someone substitute for me. So I just thought I would give you the heads up. These are the upcoming conferences for September and October. So September, the next one will be the 11th, because September 4th is a Friday, but I'm on service. 11, 25, then October is going to be a great month, 2, 16, and 30. Okay, warm up. We always warm up. And let's start with a genomic alteration IPR. All right, now what I'm going to do is I'm going to run through the slides, just advancing them slowly. And this is not a single image IPR. It's a composite image IPR, but I'm going to show the slides one at a time, so you have time to see the full view, take it in, and then I'm going to ask for a diagnosis. So it is an instant pattern recognition, but this one requires a fairly sophisticated knowledge base. So I'm actually going to call this an IPR 401. This is senior level, maybe even honestly faculty level or oncologic neuropathologist level IPR. Okay, you ready? That's fantastic, because if you don't recognize it this time, you will the next time. Okay, here we go. I'm going to start off by showing 3 or 4 H&Es. And what you should be doing is just taking in the morphologic features. And we're going to talk about them right after I show the diagnosis. But you're just taking in all the features. All right, let's go to the next one. You should have picked up that there is an additional feature that just popped up. And we're going to back off a little bit. There's another pattern that you are picking up here. Hint, it's not the tumor cells. It's something else. This is a pattern. Your brain's registering it. Diagnostic radiologists and surgical pathologists are expert pattern recognizers. We're really good at it. Okay. And then here is the last. This is the last of the 4 H&Es. Again, there's another pattern here. This is all the same tumor, just different areas, slightly emphasizing in the different areas one or another feature over the other. All right. And there are all 4. All right, in miniature, and you're taking in this pattern. Now here, listen, here's the bottom line. If you are familiar with this entity and with the histology, you already know with a very high index of suspicion what the diagnosis likely is. At the very least, there's a very interesting molecular signature defined entity, which should be at the very top of your list. All right, now we have one more piece of the puzzle, which is going to lock it in. Right, and that will be next generation sequencing. All right, so this is the NGS. These are only the altered genes showing you. Let's give you a second. Give you a second to take it in. All right, and now I'm going to make it. If you already know, then that's pretty cool. If not, I'm going to help you out to what you should be focusing on. This is the key. And part of what we do with this massive data, the massive data that's in a typical MR imaging study set for any one of our patients, massive amounts of data. And if advanced brain tumor imaging sequences are run, even more. And part of the trick, part of the skill is being able to pick out the critical things in this sea, this ocean, this forest of detail, what's really important. This gives you, this locks it in. All right, so there's a signature that's key. And now finally, this is the IPR. This is the IPR, and it consists of the histology plus the critical, one of the critical molecular signatures. All right, now I'm going to ask for the diagnosis. And so this is one of those, I think, where you either know it or you don't, or you know what's going to be highest on your list for the differential. All right, ready? Here we go. This is an FGR FGFR3 TAC3 fusion glioma. It could be any grade, grade 2, grade 3, grade 4. Histologically, you might have called it diffuse astrocytoma. It could be, some of them are grade 2 by classic histologic features. Some of them with elevated mitotic activity, you would call anaplastic astro by the classical histologic feature set grading. And some would have vascular proliferation and necrosis, including with pseudopalisading around the foci of necrosis, and those would be called glioblastoma. That was the old era. We are in the new era of molecular signature defined entities, and this is a really nice one. It only accounts for about maybe 3% of all diffuse astrocytomas. It is an astrocytoma. All right, and let's have a look at it. Now let's run through it. I'm sorry, let's see, we go back one. If you look at the histology, here are the critical features from the histology that should have raised your index of suspicion sky high as to what this tumor was going to be. Number one, in the upper left, that looks like oligodendroglioma. So the first thing you should have noticed is relatively regular round to oval nuclei surrounded by cytoplasmic clearing, so-called perinuclear halos. That looks like oligodendroglioma. So maybe as a first approach, you're thinking, oh, okay, oligodendroglioma, and the signature is going to be IDH1 or IDH2 mutant and 1p19q whole arm co-deletion, and that would molecularly define oligodendroglioma. But you know I'm not going to show something that elementary in this conference, right? So we go to the upper right panel, and what you see is actually more evidence for oligodendroglioma. You see microcalcifications, and this, and if you look in the lower left panel, chicken wire or endocrinoid vasculature, this branching, delicate branching vasculature. Again, that is a feature of oligodendroglioma. So far, what you're getting a feel of oligo, but it's not quite right for oligo. Like in the panels with the microcalcifications, the halos are not classic oligo. They're not prominent enough. Oligo-esque, if you will. And then finally, the bottom right panel, these are perivascular pseudo-rosettes. Now that's ependymoma and several other tumors as well. Now, once you see these rosettes, perivascular pseudo-rosettes, that is in no way an oligodendroglioma feature. That should give you pause. Now, here's a problem with diagnostic radiologists and surgical pathologists. It's just in our nature. Anecdotally, based on our prior experience, we tend to overweight certain features with no scientific evidence. So what you could say, a person who's inclined to do that in this case would say, well, you know, I know perivascular pseudo-rosettes, but it's always a spectrum, yada, yada, yada. Essentially, I'm going to ignore that, and I'm going to focus on all the other features, and I'm just going to sign it out as an oligodendroglioma, NOS, if I didn't have any data. You know, so what about FGFR3? You know, what about that point mutation in FGFR3? That's not really characteristic of oligodendroglioma. Why don't we just ignore it and say, oh, well, this is in, why don't we write up a case report, this particular point mutation in oligodendroglioma? That sort of stuff goes on all the time, which is why you have to be skeptical of the literature. And the literature, the knowledge base, is always temporary. It's always evolving. All right. The bottom line is these features, the oligo-like look, together with the perivascular pseudo-rosettes and nuclear palisades, highly characteristic. Not present in 100% of cases, but highly characteristic of an FGFR TAC fusion glioma, which is very important to diagnosis, which we'll go into that in just a second. All right, this is the key paper. Oh yes, this is the key paper that makes that point mutation so critical. Who first recognized it? Well, we did, right here at MD Anderson Cancer Center. So you can see first author Leo Ballister across the street at UT Houston, and then the late great famous Dr. Leeds, and so Heal was a postdoctoral fellow in Dr. Ballister's laboratory, and the great emerging superstar Jason Hughes. No pressure. All right, we discovered this as a couple of odd cases, quote, funny looking glioblastomas. And I had already seen two, and then Dr. Hughes emailed me and said, could you have a look? Because he'd gotten a message, signed out a case from one of our neuro-oncologists, says, could you have a look at this funny, quote, funny looking glioblastoma? So I look at the glioblastoma, look at the histology, and its features virtually identical to what I just showed you. So then I go into the NGS. NGS had been run, and lo and behold, there's an FGFR3 K6 K650T point mutation. And I already had 2 cases like that. And it's like, oh man, this is very interesting. All right. Also note, in these 2 cases that we reported, there were also TERT promoter mutation and NF1 mutation. And here is the NGS report for the present case. This is a new case. This is not one of these old cases. Remember, I do not do that. We do not have to use old material or stuff from the literature or studies, anything like that. These are all cases from the prior week or 2 weeks since the last time I gave the conference. And you can see in this report, there were these 3 mutations. Now they don't always have the NF1 mutation, but TERT promoter, yeah, usually they do. All right, now this is from the paper. You can see the imaging, very interesting imaging, some T1 hyperintensity, usually due to hemorrhage. That's also fairly characteristic of the percentage of cases of fusion glioma that present as grade 4s or glioblastomas. And look at the histology panels below. Far left, you see perivascular pseudorosettes. In the middle panel, you get the pseudorosettes and the microcalcifications. This was a grade 4 tumor. You can see the necrosis and pseudopalisading. And if we go back to that middle panel, you can appreciate, even though it's a small image, the perinuclear halos, the oligo-like feature. So, and this is, again, it's not present in every FGFR-TACC3 fusion glioma, but it's highly characteristic. Okay, I just want to read some quotes from this paper. I really enjoyed this paper, putting it together. And it just, what it shows is the power of old-fashioned H&E, the power of H&E. It is phenomenal. Suspicion for the FGFR3 TACC3 fusion in the 2 present cases began with microscopic examination of H&E stained sections, which elicited fusion testing. So here's how it happened. For both of these cases, I was aware of the entity. I was aware of the entity for reasons we'll go into in just a second. I will show you. And so when I saw the first case, the histology, I thought, you know, I bet this is going to be an FGFR fusion glioma. And then for the first case, I emailed the patient's MD Anderson Cancer Center neuro-oncologist and said, based on that H&E pattern, I think this is a fusion glioma. It would be great if we could get oncomine testing. And she said, yeah, absolutely, let's do it. And bam, there it was. And the same thing with the second case, and the same thing, listen, to the case that I'm presenting right now. This came up on Tumor Board this past week. There would have been no discussion. There would have been no discussion of FGFR3 TACC3 fusion if the oncologic neuropathologist was not aware of an association, a concurrent alteration in the fusion glioma, which was a point mutation, an additional alteration, a point mutation, the FGFR3. Yeah? Okay. Recognition of the characteristic histologic feature set of FGFR3 TACC3 fusion glioma, and also plenty, we won't go into that today, but that they share morphologic similarities, prompted molecular testing in both cases. Okay, this is a paper, came out, you see, 2018, the fusion glioma's characteristic histologic features. And look, this is an image from this paper, and you can see monomorphous ovoid nuclei, oligo-like with halos, oligodendroglea-like, the endocrinoid, AKA chicken wire network, thin capillaries, nuclear palisading pseudorosettes. That's the characteristic feature set. All right, back to the Ballister paper. FGFR3 alterations are common in bladder cancers, about 35% of bladder cancers, but extremely rare in brain tumors. All right, the codon 650 is one of 3 somatic hotspot mutations in the gene, although it's the least commonly affected, but as it turns out, it's the most commonly affected in the FGFR3 TACC3 fusion glioma. All right, in the Cosmic database, about 200 reports mutations at the 650 residue. 3 of those were high-grade astrocytomas, all right? Specifically with the point mutation K650T, K650T, all right? And let's just skip to the very end here. FGFR3 K650E, which is the mutation in our present case, has been associated in bladder cancers and other cancers with constitutive activation of the receptor. So the 650E, which we did not find in the initial series of cases that we reported, it was a 650T, which had not been shown, but what was predicted to be pathogenic. All right, let's have a look at that. This is a very nice oncotarget paper on the landscape. You know, if you want to get a paper published, you really have to put landscape. As long as you have landscape of somewhere in the title, you're in. You're good. All right, and so if you look at the top panel is FGFR3, the bottom panel is FGFR1, 2, and 4. And just look at the top panel, you can see at the K650 residue and the G697 residue, those are the two hotspots that had popped up for the FGFR3. Now, if you get granular, look at the very top, the red box. So at the K650 residue, K650E, the substitution E, 83 events, 83 tumors, if you will. M and 81, so those are pretty close, but E is the most common, Q in 6, N in 4, and look at this, T in 4. So the two tumors, our first two tumors in the series of FGFR TAC fusion gliomas were actually one of the rarer overall point mutations, but very common within this subset. Now there's the third hotspot is the N540, which was picked up in the other FGFRs. That's how we knew about that. So the three hotspot mutations. All right, back to the Ballister paper. In an era in which stratification and treatment of brain tumors is increasingly being guided by molecular information, recognizing the possibility of an FGFR3 TAC3 fusion in an infiltrating astrocytoma is critical and may result in significant therapeutic impact. And this field is ongoing in terms of the search for more effective tyrosine kinase inhibitors. All right, so here it is. If you were not familiar with this before, and I'm speaking to the diagnostic radiologist as well as the pathologist, burn it into your brain. Oligo-like features, but also with perivascular pseudorosettes like ependymoma, right? And because mutation testing, listen, because mutation testing is far more widespread than fusion testing, what the point of the paper was, if one has a tumor that with this histology and a point mutation pops up at one of the three hotspots in FGFR3, it might be a harbinger, a red flag, a clue saying that this might be one of the fusion. This could be fusion, and have a look at it and see, and it could lead to the diagnosis. Okay, this is the entire Ballister Fuller oeuvre. I'm sure everyone was questioning how many papers are there. Well, there are 7. 7 in the series so far. It's all great stuff. Look at the top left, primary leptomeningeal. Primary leptomeningeal oligo, proven IDH mutant 1p19q coded lead. We have known about tumors that were histologically primary leptomeningeal, cerebral over the cerebral, subarachnoid space over the cerebral hemisphere. We'd known about those case reports for decades, but this was the first report with molecular proof that that's what it was. Perhaps it was originating from a small focus in the cerebral cortex, and just it was not detectable. An intraaxial focus was not detectable on imaging or by the neurosurgeon. So it doesn't matter. It probably arose from ectopic rests. We know about those as well. Isn't that cool? And then there's the fusion glioma. Let's go across the way here. FGFR1 tyrosine kinase domain duplication and polycytic astrocytoma with anaplasia. Pyloid astrocytoma. Yes, this is going to be one of the new formally recognized entities in the WHO 2020. Okay, and let's move on. Now, we cannot leave the topic of FGFR TAC fusion without pointing out that our own Brittany Parker Kerrigan, was the co-discoverer of this class of diffuse glioma fusions, and that is a super cool thing. And I think whenever our people are involved, and I know that we have neuropath fellows from other institutions, Duke, etc. It's the same way there. Wherever you are, whichever institution where you are, it's so good to be aware of the rich history, all right, of things that have been accomplished at your institution, all right. And here is Brittany C. Parker Kerrigan, scientific manager at Department of Neurosurgery, Dr. Lang's department. A fantastic scientist, fantastic organizer, super sharp, and this was a remarkable discovery. Okay, now that's a really good segue. Let's see who can answer this one. That's a good segue to what is the most well-known cancer gene that was co-discovered, very similar to the situation with Dr. Parker Kerrigan, co-discovered by an MD Anderson Brain Tumor Center faculty member. So what I'm saying is via this another fantastic brain tumor scientist, MD Anderson Cancer Center was the site of co-discovery of one of the most famous, most prevalent cancer genes. Anybody know? All right, here we go, P10. But that is not what Dr. Steck called it. I would be asking now, if we were at the 16-headed microscope, who knows what Dr. Steck called it? There were two papers that came out. This, the P10 paper by a different group, and Dr. Steck's paper, and the group I'll show you in just a second. As it turns out, P10, one, if you will, in terms that's the name it's called by, but it was a horse race. The name was Mutated and Multiple Advanced Cancers 1. MMAC1 was the name chosen by Dr. Steck. All right, this is the great Peter Steck. This is this is Michigan State website. You can see Peter Steck joined graduate program biochemistry, Michigan State 77, PhD in 81. Then came to MD Anderson Cancer Center, where he's a member of the two departments, tumor biology and Department of Neuro-oncology. Notice at MD Anderson Hospital and Tumor Institute. How many of you knew that that was the original name? That was the old name. It's still on an internal wall, surrounded 360 by buildings, but you can still see that original inscription. Anyway, and his work led to discovery of P10, MMAC1. He passed away at a tragically very young age in 2000, but his discovery lives on, his memory lives on. He was a wonderful human being, as well as a great scientist. We have every year the Peter A. Steck Memorial Lecture. So those of you that are at MD Anderson Cancer Center, it'll be virtual, I'm sure this year until the COVID's over. But now you know a little bit of the story. Who was Peter Steck and what was his contribution? And it was huge. All right, this was the paper, Nature Genetics, 1997, identification of a candidate tumor suppressor gene in MAC1, chromosome 10q23.3, mutated in multiple advanced cancers. I have to point out here, look at the neuropathologist. Dr. Langford, our own Dr. Langford, was the neuropathologist on this case. So you know what I'm going to say? I'm going to say that Dr. Langford is a co-discoverer of P10. Now, how cool is that? Yeah, so everyone that knows Dr. Langford is only one step removed from greatness. All right, in terms of P10 being the name of the gene, all right, fine. Let's go to the ultimate authority in all things scientific, Wikipedia. And look at this entry in Wikipedia, the entry in Wikipedia for P10. Phosphatase-intensive homolog is a protein that in humans is encoded by the P10 gene. See reference number 6. Is it the 6? Let's have a look at reference 6, shall we? The Peter Steck paper. How do you like that? So I would argue that Dr. Steck actually won the battle. He's the one who's getting credit in Wikipedia. All right. I also want to point out another P10 researcher from MD Anderson, now a neuropathologist. Look at the paper number 5. See this third author right here? Maria Magdalena Georgescu. Yes, that is our Georgescu, and also UT Southwestern. That's where she did her fellowship, etc. Okay, let's move on. All right, new conference feature. I actually am going to repeat one of these that I started two weeks ago. So that's kind of amazing because usually I never repeat them. I call it a new conference feature. I'm going to call this, what the heck is this? It's things that pop up, and it happens in imaging, whether the imaging is radiology or histology. This happens all the time. You see an odd finding, like, what is this? And here's the thing. What I would like to say to all of the trainees, in radiology and in pathology, whenever you see something that's funny, something that's odd, and you think, I wonder what that is, but you already have the diagnosis. You already know it's metastatic cancer. You know where the metastatic cancer is, you know, all of that stuff. Don't just let it go. Try to figure it out. If you can't figure it out, go to one of your colleagues. See if they have seen it, can figure it out. If they can't figure it out, then you go to one of the faculty. If the faculty member or members cannot figure it out, then you go to the web. You shoot an email, all right, to whoever is best in the field. All right, let's try it. You want to try one? This is outside case. That's why you see that blue ink mark. Just ignore the blue ink mark. Now, here's what struck me when I was looking at this case. This was one of a dozen outside cases, right? Just coming through on the day. We're moving through them one after the other. And it just struck me, there's like this nodularity. to it. It's almost three-dimensional, like little hills and valleys. And what kind of grabbed me is that they're evenly a regular spacing. And look, this is a little bit higher powered. Can you see it looks like kind of these dense islands and then valleys with river or something in between? Now, I'll tell you, this is a giant cell glioblastoma. So yeah, it's a giant cell glioblastoma. Great, high incidence of TP53 mutation. That's the associated. So that's not what we're talking about here. I knew the diagnosis. There's no question about that. It's this odd appearance, and I'm thinking, I haven't seen that before. What is it? All right, now here's the point where I'm going to ask everyone attending. The question is, actually, there it is. What is it? And the answer to what this odd appearance is on this slide. But it's small. It's a tiny detail. It's the clue. And there it is. This explains these nodules, if you will, or the hills and the valleys. Let's back out a little bit. Oh, it's an artifact. Yes, can you see all the angles? You can see all the angles, and it almost looks like the specimen. Let's back out some more. It's almost like the tissue is being carved up into balls or spheres in three dimensions. So first you just see the little triangles. Then as the artifact gets worse or more pronounced, you end up with spheres or in 2 dimensions, circles of tissue. It's very distorting in many ways, all right? Let's look at another case. This is a different case with exactly the same artifact. Guess what? You never see this artifact at MD Anderson. Why do you never see this artifact at MD Anderson Cancer Center? Because we do not put brain tissue and brain tumors between 2 blue sponges. This is blue sponge artifact. Brain tissue, all right, all it has for support is glia. There's no collagen. You don't have the bundles, you don't have fibroblasts, bundles of collagen. This blue sponges are great for GI biopsies. They're not good for brain and brain tumors. Super soft, they get sucked into the blue sponge, and we're already dealing frequently with stereotactic biopsies or even smaller endoscopic biopsies, and you distort that tissue, it's like game over. Now everyone has seen, it's like, is it a goblet? The visual thing, is it a goblet, or is it 2 profiles facing each other? Is the glass half full, half empty? You can look at this by looking at the spheres, right? Just see all the balls, balloons that are touching, or you can focus on the angular patterns, all right? And so you can see it 2 different ways. All right, see all the angles? That angles, whenever you see those sharp angles, triangles, that is blue sponge, and you can see how the tissue is distorted around them. I think this looks like the Lone Star State. I'm gonna call this Star of Texas. Isn't that just great? Yeah, I like that. Okay, blue sponge artifact. Authoritative resource for this, why? Practical Surgical Neuropathology by Drs. Perry and Bratt. And the best chapter in the entire book is chapter 3. Written by who else? Dr. Ballister and Dr. Fuller, Intraoperative Consultation, Optimal Processing. Here's another great, and I'm sorry, and you can see here, this is blue sponge artifact at the top, and at the bottom, you see that looks like, doesn't that look like a tire track? It looks like the tissue was run over by a car, by a truck, a dually, as we have, here in Texas. This is biopsy bag artifact. Again, biopsy bag, great for systemic cancers, tumors, biopsies, not so great for brain. And you end up with all these squares. You can either see the tire track or you can see individual squares of tissue. Okay, another good resource, Histology for Pathologists, 5th edition, Fuller, Ballister, Central Nervous System, Chapter 9. And here, you see the big red arrow, embedding sponge, one of many artifacts that we see in the brain. And it is the job of the oncologic neuropathologist to be familiar with all of them. Question, what is the most dangerous artifact? And the answer is the most dangerous artifact in radiology and in pathology is the artifact that you do not recognize as being artifactual. You take it as a pathogenic alteration. That is the most dangerous. That's why we have to be familiar with the full spectrum of these artifacts. One of the most prevalent is cautery artifact for brain tumors. Now, cautery artifact in its most severe form is easy to recognize. The tissue is totally distorted. The vessels are purple. It's unrecognizable. It's uninterpretable. That is not a problem. That's fine. The problem is further away. As you move away from the cautery, all right, the epicenter, the focus, the effect becomes less and less pronounced, but the distorting aspects will still be there. So maybe the blood vessels are no longer purplish distorted. They will be to a certain extent, but the tissue is elongated. Cautery artifact makes epithelioid tumors appear spindle cell. Let me leave it at that. And as long as you recognize it, it's not a problem. But as we all know, there's a big difference between epithelioid differential tumor diagnosis and spindle cell diagnosis. Now that you know about it, pathologists, all our fellows, trainees, et cetera, next time when you're looking at all the cautery artifact, have a look at that and see how it changes to get further away. Just a couple of other interesting ones on that list. Postal Service crush artifact. We do not see this. I haven't seen that in a while. Usually you'll see a broken slide, but it's usually just a single crack. I used to get these a lot when I was a neuropath fellow at Duke. This was actually, I think this was an MD Anderson case that came in over the transom, as we will, and the community pathologist would put these glass slides. This is cardboard, and it was a mailer. I have another slide where I show the front. See the fold here? You could fold it over, and it actually had a place for a return address and a place where you could put a stamp. No kidding. And you put this in the mail, and this is how it shows up. Most famous case that sticks in my mind, the most famous case to me from the Duke era was a case just like this, where one of these fragments, maybe it was a triangle piece, was just big enough to cover the aperture on the stage of the microscope to look at, and it was herpes encephalitis, beautiful intranuclear inclusions. Now, is that life or what? It's like one of these priceless biopsies where you have these giant Cowdery type A inclusions, herpes encephalitis, and the slide comes in looking like this. All right, that's soul killing, but it did not prevent us, myself and my mentor, Dr. Peter Berger, from making that diagnosis. I call this paraffin pox. On the right, again, this is something we see here in Texas. You're not going to get it so much in New York, but you will in August in New York. Maybe you never get it in California because California is so perfect. The weather. This is when paraffin blocks are shipped in summer in a hot state, and the bubble wrap deforms the block, and it can be so deforming that the block can't be faced. And what the histotechnicians will do is simply melt it down and re-embed the tissue and cut it. Isn't that fascinating? Yeah, that's not minutia, that's essential detail. Okay, I think that's enough of a warm-up. Let's say we move on to our first patient. Patient number one, 48-year-old female. Here is the imaging. Now, I tell you what, here is how we're going to work this. We're going to go, I'm just going to advance the slides similar to the first warm-up case with the genomic signature IPR. And I want everyone to have a look, just take in the data. And then I'm going to ask you for a diagnosis. I want you to try it yourself. Then we will go back through, all of these and explain it. Okay, so here's the imaging. What I would like, the goal is for everyone attending the conference to be able to recognize the sequences and to draw data, to draw information from it. All right, here's the next. My conference is always HIPAA compliant, totally anonymized. I have anonymized certain parts, but here it is. I want you to take all this in. We're going to talk about it again. Draw what you can from it. This is all the data that we had to go on before looking at the tissue. All right, here's the tissue. H&E, phosphohistone H3, and Ki67, MIB1 clone. Take a second and study it. Let me say that the H&E is fully representative of the entire tumor. And if you drew the proper information from the pre-op imaging, you'll recognize that. There's nothing in another area of the tumor that I am not showing you. What you see here is fully representative on the H&E. PHH3 also, and take a close look at it. Detail is important on the PHH3. And then the Ki67. All right, now we go to the molecular signature immunophenotype, surrogate immunophenotyping. We're looking at protein, looking at the protein as markers for the genomic alterations, whether they're there or they're not, wild type or altered. So the first is histone H3, H3.3K27M, H3K27ME3, ATRX, and P53. It is critical that the oncologic pathologist know whether the antibodies used against these targets are directed against the normal wild type protein or against an altered mutated protein. That's number one. And secondly, that the pathologist knows that if there's no staining, is that normal or abnormal? If there is staining, is that normal or abnormal? And it works all four ways for both normal and abnormal. You have to understand what the antibody is directed against and what the biology is behind it, okay? Another pattern. This is the next generation sequencing visual map. This is Oncomine V3. This is the platform that we use at MD Anderson Cancer Center. It's not just a list of alterations. It's very visual, and it's fantastic if you are a pathologist or a radiologist, a diagnostic imager, because we recognize patterns. And I tell you, looking at this day after day after day, case after case after case, hundreds of cases, you can pick up patterns like crazy. It's amazing. I want you to digest each of these changes. We're going to go through them. Okay, now the circled genes are altered. The genes that are not circled are not altered, right? No alteration was identified. Some may notice that a few of the genes are underlined, like BRAF and PDGFRA. The underlining is simply the genes that were requested by the neuro-oncologist, all right? And that elicits the Oncomine testing. That's all it is. Now, the circled genes are altered, but the visual map doesn't tell you the specific alteration. That comes in the section immediately below here. So here are the specific alterations of the circled genes. I'm going to give you a second to study that. All right, that's enough. Diagnosis. Okay, this is the point where we were in the multi-headed, 16-headed microscope room. I'd be asking for people shout out the diagnosis. And actually, the beauty of doing it this way is there's always going to be one person, who nails it, and then everyone else stops thinking. And sometimes they'll even say the diagnosis before I ask the question. This way, everyone gets a chance to try it. All right. The diagnosis is glioblastoma, IDH wild type, WHO grade 4. Now, the first thing you may be saying, wait a minute, this is a non-enhancing diffuse glioma. How can this be glioblastoma, IDH wild grade 4, just like that? Well, if you're thinking that, it's because you are unaware of the cIMPACT papers and what will be the new classification and grading system in the WHO 2020, the CNS 5E, the 5th edition. All right, let's run through it. All right, the sequences were 2 different levels, all axial, 2 different levels for T2 flare, and T1 plus contrast, or gadolinium. The circled area is the lesion. On T2, the lesion is T2 hyperintense. It's the right mesial temporal lobe region. It's T2 hyperintense. If you look at the middle panel, if anything, it is more intense, hyperintense on the flare, not hypo-intense. So there is no T2 flare mismatch sign, absent. Now, what does that mean? It means absolutely nothing, because the negative predictive power, that is when the sign is not there, does not mean that it is not an IDH mutant diffuse astrocytoma. It could be either. It could be IDH mutant, it could be IDH wild type, okay? And the final panel, it's non-enhancing. And so that's also important. What is the differential diagnosis? The pattern of the T2 hyperintensity, both on the T2 and the T2 flare, is that of a diffuse glioma. All right, it goes into the gray matter. It does go to the cortical surface, mesial temporal lobe, into the molecular area, et cetera, et cetera, et cetera. It's a diffuse glioma. The patient is an adult, and so that sets the context. All right, this is Proton MR Spectroscopy, or just Proton MRS for short, or SPECT for even shorter. Look at the voxel in the top panel circled in yellow. That is the contralateral normal cortex. And you can see for the MRS spectrum, this is Hunter's angle. It's an upward slanting 45-degree angle slope. Choline, creatine, and NAA. All right, up is good, down is bad. Look at the voxel now over the tumor. We have an inverted Hunter's angle. Down is bad. Down is mean hypercellularity. Increased choline, which is membrane metabolism, membrane turnover. This is going to be a cellular, very cellular tumor. Decreased NAA, which is a neuronal cell body and axon marker. The neurons are in trouble. They can't stand the heat. All right, they're out of town. That's what's going on here. Now the area under the curves it's automatically measured, and we get and generates a choline to creatine and choline to NAA ratio, and these are well within the ratio to more or less for densely cellular tumor, for higher grade tumor. Now, it's not actually measuring grade, it's measuring cellularity. And the dense cellularity, one of the things that comes, I mean, how does a diffuse glioma become densely cellular? How does that happen? Through cell division. And cell division, we see that histologically as mitotic figures, or through surrogate markers like the Ki-67 MIB1 index. So in densely cellular tumors, they are more likely to have elevated mitotic activity, which would bump the tumor under the classic features from a 2 to a 3. So, question, in this context of a diffuse glioma in an adult patient, non-enhancing, with a steeply down sloping inverted Hunter's angle and a greatly increased absolute choline and choline to creatine ratio, choline to NAA, what the oncologic neuropathologist sees in this spectrum is not just inverted Hunter's angle. We see dense cellularity and mitotic figures. That is how you read the spectrum if you are an oncologic neuropathologist. Okay, good. Let's move on. The H&E, it's astrocytic morphology. You can see eosinophilic cytoplasm, variation in size and shape of the nucleus. That's called anisonucleosis. No vascular proliferation, no necrosis. That fits perfectly with the non-enhancing character of the tumor. This is therefore either a grade 2 or a grade 3 by the classic features. The PHH3 tells you it is a grade 3 because there are 3 mitotic figures. One of them is in anaphase, right? You can see the bottom left. 3 mitotic figures. This is a piece of a 20x field. Yeah, this is plenty of mitotic activity in a single field to bump it up to a 3. Ki-67 is, we'll just call it brisk. That is a lot of labeling. Solidly within WHO grade 3 or anaplastic by the WHO 2016 classic histologic features. But we have moved beyond the histologic features as the sole determiner. It is still relevant. It still will be used, particularly in NOS, not otherwise specified cases in which we cannot get molecular signature data. It very much in play, and even for cases where we do have molecular signature, it's going to hang around for a while in the WHO 2020, the 5E, and we'll discuss that at the very end of the conference today. All right, but we are now in the molecular era, hence. So look at the very top, histone H3 K27M. The antibody is directed against the mutant protein K27M, and we see no staining, only hematoxylin, no brown. Therefore, negative for mutant protein expression. All right. The K27 trimethylation mark, all right, retained. It's normal. Right, you can see the vast majority of the nuclei are staining. All right, that's essentially negative, if you will, for alteration, because what we're looking for when we look at the trimethylation mark, we're looking for loss, which typically goes hand in hand. If this were a diffuse midline glioma H3K27M mutant, it does, I didn't show you all the cuts, it does merge into the thallus medially. Then we would see positive K27M and its obverse negative trimethylation mark. We don't see that. Okay, ATRX is retained normal. Again, the antibody for ATRX is developed is against the normal protein. So strong nuclear staining for ATRX is normal. All right, look at the P53, nuclear P53, only a minor subset, just a few cells, which essentially it's not enough. Now listen, this is important. If, let's say 80%, 90% of the nuclei were staining for P53, that would be indicative of a TP53 mutation, strongly correlated with TP53 mutation. So listen, you might think, oh, well, if that's the case, is the antibody directed against the mutant protein? No, the antibody is directed against the normal protein. How can that be if this is normal? This is what normal brain looks like, is essentially no staining. Well, if the antibody is directed against an epitope on the normal P53 protein, and you don't see any staining, how can that be normal? And how can positive staining be abnormal? And the answer is, normally, in normal cells, P53 protein is turning over so fast. This is the received, it's like received pronunciation. It's the concept, it turns over so fast that you do not see staining, all right? Except with cell division, you know, special situations like that, but not in resting G0 cells. When the protein is mutated, not always, but in a large percentage of cases, the mutated protein is stabilized. It's stabilized, it hangs around, and we visualize that with an antibody to the normal protein as strong, positive, high percentage nuclei. Now, see, you have to know the difference between the staining patterns, you know, of the antibodies. Isn't that, I mean, that is the whole key. I'm telling you that there's a lot of misconception in the community, and these stains are misinterpreted frequently. Okay, here we go, moving on. The visual map. Let's take each of these alterations. Before we look at the specifics, let's just see what we can glean from the visual map. Okay, there's TERT, that's TERT. The odds are overwhelming in a diffuse glioma, and we know it's a diffuse glioma from the pre-op imaging, from the T2 flare and the way the T2 flare is behaving, not pathognomonically, but to a high, so we know it's a diffuse glioma. It's highly likely that this is in the promoter, extragenic, not in the coding region of the gene. It's going to be a TERT promoter mutation, minus 124, minus 146. The minus means promoter region. But we do not know that until we look at the detail. It is also possible that it is in the coding region, and it may not have significance. It's an alteration, right? It could just be, it could be a SNP, yada, 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 whatever, okay? We have to look at the details. That's TERT. EGFR, now we covered this in one of the earlier conferences. We know from the visual map that EGFR is altered. We know from our fund of knowledge, our knowledge base, that there are at least 4 different major alterations that are possible in glioblastoma, and they're not mutually exclusive. Sometimes none of them there, sometimes 1, sometimes 2, sometimes more. What are examples? Point mutation in the coding, intragenic coding region, one of the exons, point mutation. EGFR amplification, EGFR V3, variant 3, could be variant 1, variant 2, variant 3, variant 4, variant 5. There are 5. Absolutely. It could be any of these. We will know when we look at specific details in a second. And now these two guys are linked. They're both on CDK4 and MDM2 chromosome 12. They're both on chromosome 12. Whenever you see them pop up like this, it's highly likely that it's going to be an amplification, because it's going to be the region of the chromosome they're on 12's amplified, and they get amplified together. All right, they're both along for the ride. All right, specific alterations. Here's the TERT. It is in fact C dot minus 124 C to T, all right, the negative sign indicating that it's in the promoter region. And so you can see under location to the right, extragenic, that means in the promoter, the gene being defined as the coding region, the sequences of introns and exons. Okay, let's go to CDK. Okay, all of these, CDK4 and MDM2 on chromosome 12, amplification as we predicted, and then EGFR chromosome 7 amplified. That is huge. All right, here are the keys. EGFR amplification and TERT promoter mutation. Either one of these would have been sufficient to call this tumor glioblastoma. Once we know it's a diffuse astrocytoma in an adult, this is glioblastoma, IDH wild type from the NGS because of this. All right, where does that come from? Here we go, the cIMPACT papers. We will continue to talk about the cIMPACT papers until later this year, just a few months really. The 5th edition W2020 comes out. So cIMPACT 6, Diagnostic criteria for glioblastoma IDH wild type. Okay, now wait, what does that header say? It says what we're about to discuss here are the criteria for rendering this diagnosis up front, just glioblastoma IDH wild type. All right, there's the paragraph. It says see table 5. Here's table 5, suggested criteria which will be adopted in the WHO 2020 for making this diagnosis. An IDH wild type diffuse astrocytic glioma. Let me add here, in an adult. Pediatric tumors are different, and we will discuss those on September 11, which will be the next conference. That's going to be the next WHO thing that we're going to talk about. In an adult, so IDH diffuse astrocytic glioma, how are you going to know that? Well, our first indication is going to be the imaging, the T2 sequence, T2 and T2 flare sequences, or any flavor. Let's say you don't have all that, maybe just have a gradient echo, all right? Fine. IDH wild type diffuse astrocytic glioma in an adult with vascular proliferation or necrosis. That's WHO 2016. We already knew that, right? And that usually it's going to correspond to robust, not wispy, faint, focal, but in your face enhancement. All right. Or here's the new, or one or more of the following molecular features: TERT promoter mutation or EGFR gene amplification. Note, it does not say EGFR V3. No. That will not do it. Or one of the point mutations. That will do it. It's gene amplification, which is most highly associated with IDH wild type glioblastoma in this context, or classical cytogenetics. Gain of 7, loss of 10. Gain of 7, most important glioma gene on 7, EGFR. Most important gene on chromosome 10. Loss of 10, we've already talked about it. Must be a tumor suppressor. P10. That's easy to remember, 10, P10, or as we say at MD Anderson Cancer Center, MMAC1. Actually, no one says that anymore except for me. Now look, it says one or more. Why does it say or more? It could just say one of the following, but if it says one of the following, you know there's going to be some guy. There's going to be some guy out there that says, yeah, I know it says one of the following, but I have 2 of them, or I have all 3. Does that count? Yeah. So we're trying to make it idiot proof, okay? That's sarcasm, and I am sarcastic against myself as much as I am other people. So there it is. There's the key right there. Diagnosis for this non-enhancing diffuse astrocytoma, glioblastoma, IDH wild type diphtheria grade 4. What if this had been a resection of an anterior temporal lobectomy for a diffuse astrocytoma? All the tissue was put through. It was all looked at. Mitotic figures were extremely hard to find, and the Ki-67 MIB1 labeling index was 3%. But it had one of these 3 alterations. What do? You call it glioblastoma, IDH wild type grade 4, done and done. Does that make the point? Yes. Diffuse astrocytoma, IDH wild type, grade 2, and anaplastic astrocytoma IDH wild type, grade 3, do not exist. They do not exist. They exist, I will modify that. They exist for a very brief period of time at the very beginning of the evolution of the tumor. Let that sink in, and we're going to cover it again at the very end of the conference. All right, and that's coming. I know some people are saying, well, look, it's 3:56. How long is this guy going to keep talking? I'm going to keep talking till I finish it. I think I went an hour 45 their time. We're not going to go hour 45. We're going to finish in about 5 or 10 minutes. Okay. All right. Now I draw from all of the conferences, all of these resources at MD Anderson Cancer Center. I draw from adult tumor board. I draw from pediatric tumor board. I draw from all of the outside cases coming in, all of the in-house cases. Here's a case from this morning's Baylor Neurosurgery case conference. And I want to give credit to Dr. Nisha Gadgil, Baylor Neurosurgery resident, PGY 7 years. That's right. That is how you generate excellence in a field. And she's currently a rotating chief neurosurgery resident, MD Anderson Cancer Center. All right. Dr. Gadgil presented 2 great MD Anderson cases this morning. Let's cover them. 41-year-old female. Here's the smear, cytologic smear preparation. This is always where we start. There are only 2 patterns of smears. Actually 3 patterns of smears. One is no cells. No cells. That's not a good smear. That tells you probably should have done a scrape, etc. But it also tells you that if there's tumor there, it's being tightly held by the tissue, and that can be informative. The second pattern is single cells, just a smear, a beautiful smear of single cells, like in lymphoma, medulloblastoma, central neurocytoma. And then the third pattern, chunks, clumps, which is due to either intercellular junctions, desmosomes, if you will, or long intertwined, intertangled cell processes like in a sarcoma or solitary fibrous tumor, or both, desmosomes and long cell processes like in meningioma. So this is definitely chunky, and here's the high power on the smear, and this is telling you volumes. All right, I want you to analyze this smear, and it looked the same everywhere, exactly like this. So taking these features, all right, here's the question for you. What does the pre-op MR imaging show? All right, now let's move back for just a second. I'm going to accept one of several different patterns. Actually, there are four different imaging patterns, four different imaging patterns that I will accept as a correct answer. All right, what do they show? And here it is to look at again. Anybody have a clue? Obviously, I hope that you're thinking glioma, because of these fibrillary, long, elongated cell processes, okay? Now, here's where you can't get sloppy. So far, all we have looked at is just one domain of the information in this smear, the cytoplasm. Is it absent? Is it vacuolated like perinuclear halo? Is it epithelioid? Is it long, elongated like fibrillary? Is it really elongated like pilocytic, hair-like? That's the cytoplasm. And what we have is fibrillary, or long processes. What about the nuclei? We also do smear to look at nuclei that are not distorted, not altered. And what should be, listen, what should be striking you about these nuclei is their uniformity. They are magnificently uniform, oval, really. They're not quite round enough to be oligo, and it's not oligo anyway because there's too much, these couldn't all be reactive astrocytes, right? So we know it's glioma, but those magnificently uniform oval nuclei is highly characteristic, like seen in not all cases, but we'll call it 90% of cases of one specific tumor. Which tumor is that? And the answer is ependymoma. Now, this is where some experience comes in, because if you didn't have an experience and you're looking at this, you're saying, oh, look at all those fibrillary cell processes. This must be an astrocytoma. And that's why I wanted to show this, because you should also, because the point is ependymomas at any location mimic astrocytoma with respect to the cytoplasm. But very few astrocytomas are going to be this cellular with this low degree of regularity. Everybody got it? Okay, now this one, what are the patterns that I would accept? If it is a supratentorial ependymoma, you could say an intraventricular mass in the ventricle. Or you could say, if it's supratentorial, a well-circumscribed mass in the cerebral hemisphere, extraventricular. Absolutely. This is called half more or less of ependymomas, supratentorial, have no connection to the ventricle. Now, I know I'm not talking to the neuroradiologists, the faculty neuropathologists, or the neuropathology fellows here. I'm talking to, if we have any attendees that are really green and might be thinking that ependymomas must be in the ventricle. Supratentorially, a huge number of them, probably most, are actually not in the ventricle. Infratentorially, you could have said this is a fourth ventricular tumor. What I would have liked even better, because all ependymomas in the fourth in the posterior fossa or in the ventricle, what I would have liked better is a fourth ventricular mass that is growing out through the lateral foramina of Luschka and plus or minus the median foramen of Magendie. Or if you're in Texas, Magendie. Magendie, yeah, okay, right? That's plastic ependymoma, highly characteristic. Or what's the fourth pattern? If it's, I'm sorry, I'm gonna have to make it 5. If it's in the spinal cord, intramedullary in the spinal cord, you would have said it is a well circumscribed mass in the center on cross sections in the center of the spinal cord, surrounded by a rim of viable cord, probably with a syrinx, or let's call it a space above and below. Or here's the 5th pattern. I should have said 5 patterns. If it's in the lumbar cistern, it will be a circumscribed mass ranging from spherical to elongated boxcar or sausage shaped. That's the full range of morphology in the lumbar cistern, arising from either the conus medullaris or most commonly filum terminale, or least commonly one of the spinal nerve roots, and that'd be myxopapillary ependymoma, and that's what this case is. So in this particular case, this is myxopapillary ependymoma. There you can see it, boxcar, arising right at the junction of the filum with the conus. That's going to be the single most common location. And you can see on the right, filum going all the way down. Burn this into your brain again. These are ependymoma cytologic features. Can mimic astrocytoma. Be careful if you don't already have the imaging. Now, of course, in our world, we're going to do everything we get to get the imaging or description of it, but it is very useful. Listen, it is very useful to go through these exercises like we're doing right now, starting with the smear, and see how far you can get. That is how you hone, you sharpen your powers of observation and your diagnostic skills, whether it's radiology or pathology. All right, here's the formalin-fixed paraffin-embedded FFPE tissue section, and you can see the perivascular pseudo-rosettes, and they're just beginning to develop these little blebs of mucin accumulation, this myxoid material. Those in many tumors, most myxopapillaries, will continue to gather until it totally crowds out, obfuscates, obscures the fibrillary processes of the ependymoma, and that's what produces these big myxoid mucin cuffs, and there will also be myxoid mucin microcysts. Now listen, this is the best myxoid area of this particular tumor that I can find. Most of it was solid. Here's the point for the pathologist. The myxoid content of myxopapillary ependymoma varies from virtually none to comprising 75% of the volume of the tumor, right? Big bags of mucin myxoid material. That is the spectrum. You simply need to be aware of it. Now let's address another issue. This is the current patient, and what I'm showing is the true border of the tumor, and that's just pia. It's a very thin layer of pia. That is the quote capsule. In many cases, it appears to be intact. That's the best outcomes follow from that. In others, it's already out of the bag. It's already spread. Typically, the way that you will see that with myxopapillary ependymoma is you look to the very bottom on the spinal cord imaging. Look at the very bottom of the thecal sac, and just because of gravity, if you see contrast enhancing stuff down there, that's going to be disseminated myxopapillary ependymoma growing. Sometimes there will be nodules on the roots of the cauda equina. That's dissemination. That can happen before the patient even presents. It's a big problem, unfortunately. Okay, now why is there a significant incidence of treatment failure with myxopapillary ependymoma? It has to do with a neuroanatomy, the eccentric anatomic location central canal. Here's the bottom line. Intramedullary, within the spinal cord proper, the central canal, ependymal cells, which are the putative origin of ependymomas, are in the center. It's the central canal, not in the filum. And you would not know that. And the filum is the direct continuation. It really is intramedullary. It really is it's inside the pia. It's surrounded by pia. Developmentally, it's intramedullary, and there usually are still neurons and a little bit of neuropil, at least in the filum terminale internum, all right, in the part in the lumbar cistern. Anyway, but traditionally we say it's extramedullary because it's below the conus. Fine. As long as you know the truth. Now, here's the point. The point is, during developmentally, the central canal has an opening. It's called, the caudal neuropore. It comes very superficial. Let's look at a couple of normal human filum terminale in cross section. Here it is. Circled area is that's the central canal. How central does that look to you? By the way, you can also see from this that the phylum terminale is 90% collagen. And then you can see a large artery and a couple of veins. Those will be the spinal arteries in the vein, a big blue vein. That's neurosurgeons can recognize that intraoperatively. This is a second example, just a different example, cross-section of normal human phylum terminale, internum, collagen, the big vein. You can see in the center, two little arteries. There's in the far right, there's a nerve, a small nerve fascicle. That's how schwannomas of the phylum arise. And then again, very superficial is the remnant of the central canal. Now imagine myxopapillary ependymoma starting right there in that location, just beneath the pia. Look to the far right of the screen. Do you see that little layer, all broken up, kind of artifactual? That's the capsule of the phylum terminale. That's the pia. All right. Imagine the tumor originating there. How easy is it going to be for it to break through? Now, many do not. Thank goodness, or we would have 100% dissemination and all the morbidity and ultimate mortality that goes with that over a decade or two. All right. But many do, and it's easy to understand why. Oh, by the way, there are case reports of myxopapillary ependymoma originating, at least macroscopically, under the loops from a cauda equina nerve root, not the phylum. They're attached to the nerve root. It's easy to see how that could happen. Either a remnant of that neuropore, that caudal neuropore, or the tumor starts, it breaks through early on. It's got all this space to expand. Why not latch on to a spinal nerve root? It's easy to understand once you realize that the central canal is not central in the phylum. It is so elementary. It's so elementary, but how common is that knowledge? I would argue not very common, because who studies that? You know who studies that? Oncologic neuropathologists study that. Experts study that. Specialists study that. And that's what we do. Diagnostic neuroradiologists, diagnostic oncologic surgical pathologists, we know stuff. And sometimes that stuff can explain things. How beautiful is that? All right, now in this particular case, Dr. Gadgil did identify a nerve root that looked like it potentially, along with Dr. Weinberg, a nerve root potentially involved. Now what I'm showing you here is the nerve root, and in the background, most of the substance here is peripheral nerve, and you can recognize that as peripheral nerve, easier to see, higher power. And between the two blue dots is a little bit of myxoid stuff. On the right, by the way, we know that this is a sensory nerve root. Now, Dr. Gadgil had identified it as a sensory nerve root, based on stimulation. All right, that's super cool. No motor response. How did I identify this as a sensory nerve? How does the oncologic neuropathologist identify it as a sensory nerve root? We can't stimulate the dead tissue. Well, here are 3 different dorsal root ganglion cells that were present in the tissue section. Now, the dorsal root ganglion cells are not always collected all together in the dorsal root ganglion. In fact, it's very common for a few of them to be scattered along the root, all right? Both intradural, extradural, and that's exactly what we see here. So I knew immediately that it was a sensory nerve root histologically. Now, this, and there it is, a cauda equina sensory nerve root. Now, that little bit of myxoid material was not enough to call a myxopapillary ependymoma. The reason is, with pathologic processes in all tissues, virtually all tissues, there can be myxoid degeneration as a common stromal change. We had to prove it. How do I prove it? Well, the easiest way is just deep stepped sections, okay? And this is just showing a high power, strongly suspicious. And, honestly, I probably could have called it based on this, but why not be sure? So what we do wide interval. It means a lot of space, a bunch of microns, in between, deep step sectioning. And here's what we see: unequivocal myxopapillary ependymoma. There are those oval nuclei, a solid substance with, the fibrillarity, the myxoid microcyst. Done and done. We have now proved, CSF dissemination of the tumor in this particular case. Diagnosis: myxopapillary ependymoma, WHO grade 2. All right, not grade 1, grade 2. Notice also, is that a Roman numeral? No, Roman numerals are out the window. Neuropathology has finally decided to join the fold of the rest of the blue book, if you will, the WHO tumor books, and use Arabic numerals. So we're going to Arabic numerals. It's about time. All right. There are 7 cIMPACT-NOW updates, all of which mirror or show, they don't mirror, they are reflecting the changes to come in the WHO 2020. Here is the most recent one. I think this is finally the last, advancing molecular classification of ependymal tumors. Here's the new molecular classification. Classified first by anatomic compartment. Anatomic compartment first, supratentorial, posterior fossa, spinal, and then subependymoma bridges all 3, so it gets a separate category. Then by molecular signature. The 2 identified supratentorial critical molecular signatures are C11 ORF, 95 ORF. That's open reading frames. We don't really know specifically what it does. We have some clues of the function now. YAP1 fusion positive. That was REL A for the C11 ORF 95, but C11 ORF is the more frequently occurring fusion partner. So this is the new name. All right, for REL A is the old name, new knowledge. Is that good? Yes. Posterior fossa ependymoma, posterior fossa group A, or subtype A, that's pediatric type, and group B, adult type. And group A tends to have more of an aggressive course, but there's still some dispute. It's not locked in. That's why you do not see a grade. Look at the WHO grade rubric to the far right. Note that for the molecular defined ones, there is no grade. That's because it's still sub judice, or judice, if you like the Latin. It's still in the courts, still being decided by the courts, by the experts. If we want to give the C11 ORF 95 grade 3, make the YAP grade 2, we'll see. And then same thing for the PFA, PFB. All right. However, if you do not know molecular signature, look at the just supratentorial ependymoma. It's not here, but you could put NOS, not otherwise specified, if you don't have data, or if it's a different molecular alteration besides C11 ORF and YAP1, you could put NEC, not elsewhere classified, because you do have data. For those, the NOS and NECs, still we're going to keep the old histologic feature-based classification. So we'll call them either a 2 or a 3. Now again, the diagnosis would be supratentorial ependymoma, NOS, WHO grade 2, or WHO grade 3, using elevated mitotic activity, vascular proliferation as primary criteria for bumping a 2, 2, or 3. Same thing with the posterior fossa. Myxopapillaries are all 2s. Listen. There is such a thing as myxopapillary ependymoma with anaplastic features. It is uncertain if they behave more aggressive. They're very rare. Not enough data to make a call on that. That's why right now all grade 2. And mercifully, some things never change. Good old subependymoma, cured by gross total resection, WHO grade 1, no molecular signature to worry about there, etc. That's it. All right, and here's our myxopapillary ependymoma. I've shown this several times in the conference. I'm showing it again. Now listen, if someone emails me and say, there's nothing new in this conference, I've already seen this before, I'm gonna hunt you down. Yeah, I have skills that are a nightmare for people like you. Now, I'm being facetious. It's very important to reiterate the spectrum. Now notice the first 2 cases on the left. These are myxopapillary ependymomas, which are tiny, probably incidentally identified, but in other cases they were symptomatic because of the root involvement. They are spherical. They look exactly like, in terms of their shape, they look like clear cell / sclerosing meningioma, which that type of meningioma in the lumbar cistern is not dural based, no dural tail. They're originating from the arachnoid cells of the arachnoid trabeculae, connecting all the roots of the cauda equina. All right, so if a spherical tumor like that, you have to keep myxopapillary ependymoma in your differential. And of course, do not forget clear cell, sclerosing, fibrosing meningioma. And then all the way up, all right, these are 10 different patients, all the way up to the very large ones. You may recognize our current patient as 3rd from the right. That's the patient we're considering today. All right, second case. We're only doing 2 cases. Here we go. Keep going. 25-year-old female. This is the second, Dr. Gadgill's second case from the tumor board this morning. We're gonna make it really quick. Here it is. I'm showing you T2 flare, T1 plus contrast diagnosis. All right, done and done. Yeah, I know. But listen, if even one person in this conference does not know the T2 flare mismatch sign, then it's worth going through it. T2 flare mismatch sign in the context of an adult with a diffuse glioma. How do you know it's diffuse glioma? Again, from the T2 flare into the overlying cortical ribbon of the peel surface, or going deep into the thalamus, into the basal ganglia, not being confined to internal capsule, external capsule, etc. That's diffuse astrocytoma. Patient's an adult, T2 flare mismatch sign, positive predictive value. Here it is, 100%. That's highly specific, 100%. There's the validation study, 100%. PPV. Negative predictive power, pretty lousy, which means if it's not there, it could be either, it might be mutant, might not be mutant, you don't know. Again, the spectrum, 8 different patients showing T2 flare mismatch sign from MD Anderson Cancer Center, all tissue proven, IDH diffuse mutant, diffuse astro, either grade 2 or grade 3. All right, here's the current patient. The current patient, we're looking at H&E, clearly astrocytic, all the great fibrillary processes, microcysts, which are much more common, you know, in the lower grade tumors as opposed to glioblastoma, which means IDH mutant tumors, which are for the most part grade 2, grade 3, except for the secondaries, which can evolve to a 4. Elevated mitotic activity was present, no vascular leaching, no necrosis. So this is a WHO grade 3 by WHO 2016 histologic feature-based criteria. Anaplastic astrocytoma, WHO grade 3 by classical features. Here's the molecular classification. I just love this, showing the C of IDH1 mutant protein. The canonical mutation R132H, there's the higher power. You can see it's not just artifact anything staining. You see the blood vessel in the center with the translucent red blood cells, and the endothelial cells surrounding them are negative, just the hematoxylin staining. The beautiful thing for us as diagnostic oncologic pathologists about IDH1 or 132H antibody, and about the biology, the expression is it's essentially 100% of the tumor cells express the mutant protein. So if your image stain is working well in your laboratory at your institution, you can pick up single cells way out distant with a high degree of confidence that that's infiltrating tumor. P53, strongly positive in a very high percentage. You see the microcyst, that is indicative of a TP53 mutation. Here's the ATRX. Again, we have the internal positive control in the center, that's the endothelial cells, and then there are scattered normal astrocytes, oligodendrocytes, microglial cells that are staining. The vast majority of tumor cells, you only see hematoxylin, so ATRX loss in the glioma, indicative of an alteration. It may not be a mutation, could be post-translational processing, other mechanism. So this is the classic molecular alteration triad of IDH mutant diffuse astrocytic disease. Now again, we already knew the diagnosis was going to be IDH mutant from the T2 flare mismatch sign in an adult patient, right? But this is confirmation. What is the triad? Either IDH1 or IDH2 mutation, TP53 mutation, and ATRX loss of protein expression. Now I'm saying that, why didn't I italicize it, make it a gene, and say ATRX mutation? Because it's not always a mutation. It can be a post-translational modification. Multiple different mechanisms can cause loss of immunoexpression of ATRX protein. So listen up. This is a great example of where a robust immunostain is more sensitive, all right, and reliable and predictive than mutation screen, than next generation sequencing. How cool is that? Now, what's the setting? Here's the setting. The setting would be this exact tumor, T2 flare mismatch, and then the IDH132H is strongly positive, great. P53, 99% of the cells, great. TP53 mutation, but the ATRX, you look at the ATRX, it's lost, but then on the oncomine, there's no mutation. No mutation on the oncomine, but the ATRX is lost, that's fine. And there's no discrepancy. There is no discrepancy between loss of expression, immunoexpression of ATRX in histology, and absence of a mutation on a next generation NGS profile. But once you understand that there are multiple mechanisms. Now, by the way, if there's anything at all, any questions about ATRX biology, I would suggest that you email Dr. ATRX, AKA Jason Hughes. He knows all about this gene and more, one of his primary areas of research. All right, so this is New England Journal of Medicine, 2015, lower grade gliomas. Look at the red boxes. This is what we're talking about. Lower grade, which is grade 2 and grade 3. Anaplastic is no longer high grade, only 4 is high grade. Now with the molecular, anaplastic is lower grade. IDH mutation, 1p19q code deletion absent, meaning it is not an oligo. Look at the red box, TP53 and ATRX alterations, astrocytoma, IDH mutant. Okay, anaplastic, so the 2016 diagnosis, anaplastic astrocytoma, IDH mutant, WHO grade 3. Let me add just a quick footnote here. In many cases, ATRX can be lost, the expression, and there's no mutation. In probably most cases, there is an ATRX mutation. So don't take that there usually is not. Many cases, most cases, there is. Okay. All right. WHO 2016 diagnosis for this case: anaplastic astro IDH mutant WHO grade 3. We do not use that diagnosis anymore. cIMPACT Update 5 recommended grading criteria and terminology. That's the name for IDH mutant diffuse astrocytomas. It was reiterated in this big overview, cIMPACT 6. Here's the table of IDH mutant astrocytomas. They are all, no matter what grade, including 4, they are all called astrocytoma. No diffuse, no anaplastic, no glioblastoma. Followed by IDH mutant, followed by the grade based on the classic histologic criteria for now. All right, we'll see how that goes. In the present case, it falls into the middle rubric. Astrocytoma, IDH mutant, grade 3, a diffusely infiltrated astrocytic glioma with either an IDH1 or IDH2 mutation that exhibits focal dispersed anaplasia. That's not really essential, and displays significant mitotic activity. It's still subjective. That's what that little, the superscript A, the footnote A, there's a whole discussion of mitotic activity. It's subjective. There is no cutoff. It's probably 2 mitoses if you want to be the least stringent. People bump them up. It's subjective. Hopefully it will disappear. We need a better study to prove it. And now here's the key. Microvascular proliferation, necrosis, and CDKN2AB are absent. The presence of CDKN2AB, just like necrosis or vascular proliferation, will upgrade a 2 or a 3 IDH mutant diffuse astro in an adult to a grade 4. The molecular signature alone is sufficient. You don't need the histologic criteria. So the WHO CNS 5th edition 2020 astrocytoma IDH mutant WHO grade 3. Now in this particular case, there is a qualification that should be given in the comment. We do not know for this particular patient the CDK2 and AB status. We don't know. If there is homozygous deletion, it will pursue a more aggressive course, and we would bump this to a 4, a grade 4 tumor. If that's present, we don't have that data, we don't know. All right, second caveat, the prognostic power of histologic grading by the classic histologic features is, there it is. This is the big buzz term at the meeting. For which the cIMPACT 6 came out in Utrecht in the Netherlands, subjudice. Judice is the modern English version. Judice would be classical Latin. You say it either way you want. It means it's still in the courts. It's still under judgment pending, which means the experts are still thinking about it. I am hoping, listen, I am hoping that we will ultimately be able to get rid of grade 2 and grade 3. From this disease, because listen, this is anecdotal, but everyone has seen it. We have examples of patients coming into clinic with 15 to 20 year histories. They were diagnosed 15, 20, 25 years ago with a grade 3 anaplastic astrocytoma, and we have a few examples of glioblastoma 20 years ago. Those were IDH mutant tumors. We did not know it at the time. That explains it. Now you're going to grade, so you're going to call it grade 3, all right, or grade 4, and the patient may have a 15 or 20 year survival. Does that make any sense at all? But again, it has to be science-based. Everybody got that? Okay, now this is it. We're just going to take one more minute, because I said I was going to do this. This is the new conference feature from 2 weeks ago that I said I would reiterate it, and I will reiterate it. The CNS 5E, just stuff to anticipate, and it's based on the literature. All right, what we covered last time, for any of you who missed the conference: bithalamic glioma, EGFR mutant, childhood, adolescence primarily. It is a diffuse astrocytic tumor. You have to have major involvement of both thalami at presentation, not just a little bit of massa intermedia crossover. The genomic, 2 recurrent genomic alterations, both in EGFR, small in-frame insertions, exon 20, which is intracellular tyrosine kinase domain, or missense mutations, exon 7, which is the ligand binding domain. Okay, that was the last one. Here's what I want to discuss for just 1 minute, 60 seconds. This is a concept, not an entity. Remember how we talked about earlier, ependymoma, the concept of ependymoma classification has changed, all right? And it's changed in that we will classify ependymomas based on compartment first. Supratentorial ependymoma, comma, in the molecular signature. Posterior fossa ependymoma, comma. Spinal cord, spinal ependymoma, comma. All right, for the diffuse gliomas, this is the astrocytoma oligodendroglioma spectrum. Finally, the data and understanding of pediatric diffuse gliomas has matured to the point where we can not only pull out one little entity or two little entities, like the diffuse midline glioma H3K27 mutant, we can try to attack the whole body of all pediatric, mean childhood and infancy, first year life is a special case. Now, the concept is adult type diffuse gliomas and pediatric type diffuse gliomas. Now, why isn't it just adult diffuse gliomas and pediatric diffuse gliomas? Because there's overlap. There always is overlap, right? It's like if it's a Gaussian distribution, all right, for the age incidence, a normal distribution, the tails will overlap, right? So we'll say adult type. So it's possible to have an adult type diffuse glioma, certainly in a 12, like a IDH mutant in a 12-year-old, 13-year-old starts essentially at puberty, right? That happens. But that would be an adult type diffuse glioma in a child, in the same way pediatric type. But the predominant population is what we're talking about. Okay, that's the first point. Got it? Okay, now I just want to take 1 second to look at conceptually what this means and why are we doing this. Now, the next conference, which will be September 11, we're going to look at the pediatric type diffuse gliomas, which is huge changes coming. But let's look at adult type. It's just as stunning. All right, let's put together, let's aggregate the WHO 2000 and 2016 classifications, because I want to include the oligoastrocytoma, the mixed glioma. These were all of the diagnoses possible if you combine WHO 2000 with what we know about IDH mutant and wild type, right? Diffuse astro, IDH mutant grade 2, IDH wild type grade 2, anaplastic mutant wild type, glioblastoma mutant wild type, oligo mutant, anaplastic oligoastro, anaplastic oligo. All of those were categories, if you will, of disease, categories and grades. What does it look like if you take all the knowledge, everything you know right now about IDH mutant versus IDH wild type, diffuse astrocytoma, and about oligodendroglioma? How many different diagnoses are there really? 3, only 3. This is what it looks like. Astrocytoma IDH mutant. We just talked about the fact that we have anaplastic astros and some glioblastomas that have lived 20 years. That would be a long-term survivor. And it's easy, we know why now. They were IDH mutant. Why should we be grading? But this is the disease, and we're going to continue to grade them until we can eliminate it. But that's one disease, and it's totally separate from glioblastoma IDH wild type. Now you would say, but wait, where is diffuse astrocytoma IDH wild type grade 2? Because the tumor is not enhancing, and there's no vascular proliferation, there's no necrosis. But if if it's IDH wild type in an adult, we're talking about adults only, and it is a classical diffuse glioma, it's not one of the other exceptions that you need to rule out, it will behave like a glioblastoma, the vast majority of cases. There's always exceptions to everything, right? But in the vast majority of cases, there's only one tumor, and the classic grading is fruitless, and it's misleading to do that. The molecular signature is going to determine the course. So that's a disease. And then for oligo, it's the same thing. We've always known you're flipping a coin for the most cases with oligo, with anaplastic, oligo grade 2 versus grade 3. A lot of times it is. And when we use vascular proliferation and mitotic activity, but again, that's subjective. But you think about it conceptually, there are only 3 diseases. Now, you know what I love about this? What I love about it so much is that, look at that. How complex and difficult is this compared to this? And the principle that I love so much is in this era of expanding next generation sequencing, and we're using 8 Venn diagram data spheres, we have to do that to put all these together to get precise diagnosis. With all this increase in complexity, some things with our understanding are getting simpler. They're getting simpler, and this is one of them. We understand the diseases now, and it's simplifying things for us. Isn't that a wonderful thing? Okay, I think that is a great way to conclude. Next up with this particular thing, September 11, we'll talk about pediatric type. I think that's it. We went an hour and a half. You got your money's worth. That's what I'll say about that. And with that, I think we'll end the conference. Thank you so much to everyone for attending, because if you did not attend, there'd be no conference. So I will see you next conference, September 11. Thank you.